Now I'm going to introduce strings. But first, let's review the char data type. In another video, I said that the C89 standard provides for 4 integer types: the char, the short, the int, and the long. And the primary difference between those 4 is how much memory is allocated for storing the integer you wish to store. The char, though, is the smallest of those, and it only gives you 1 byte of memory. 1 byte is 8 bits, and 8 bits is 256, which means that it can only represent 256 distinct values. So what would be the use of a 1 byte integer type? We can still use it to store what you think of as regular numbers, but its primary use is for representing characters. The syntax for using it, though, is just like other integer types. I have a variable type, char, a variable name, 1 letter, the assignment operator, and then in single quotes, I write the character I wish to store. Now internally, there is no symbol D that's being stored. It still gets converted to a numeric value, but it's easier as a human writing this to write capital D if I mean capital D. So what characters do I have available to me when I do that? The characters I can use come from what's called the ASCII character set, or at least without some other work. Note that the A in ASCII is American, so a lot of the characters we see will be somewhat specific to American English. If you need to represent other languages, then newer languages provide unicode support. When I save something as an ASCII file or in the ASCII format, I'm creating what's also called plain text. Your programming editor that you use to write all your C code saves its file information as plain text. So it's already doing this. If you come from the Windows world and have used Notepad, Notepad saves in plain text. So this is not unusual, but this is probably the simplest of the file formats. So this is different than something like Microsoft Word's doc format or Microsoft Word's Excel format. Those are what we call binary formats, which is quite different from this. The nice thing about plain text is you can just open it up in an editor and look at it. So what characters do we have available to us when we're using ASCII? This column and then these 3 right here are the ASCII characters. As I state here, there are 120 ASCII characters. Since a char can store 256 distinct values and 128 is half of those, then we can store our characters as chars, or that is the ASCII characters can be stored as chars. So the symbols you see over here are often referred to as non-printable characters. So we have things like there's a character that actually represents a backspace. Putting this in your code can actually cause the backspace to operate. There's a bell character. Putting this in your code can actually make your computer make a bell sound. When we write \n in a printf statement to produce a new line is actually an abstraction because on different operating systems, the underlying characters that represent a new line are different. On Windows, it uses a combination of a line feed and a carriage return. On Linux, which is what I'm using here, it just uses one of those 2 characters. One of the things we need to know about, and we'll see here in a moment, is the null character, which has an ASCII value of 0. This column right here, in each of these larger columns, are the decimal values for the ASCII characters. So if I put a space character in my string, internally it's represented as 32, but of course in binary. Here's the digit characters. Don't confuse these with traditional integers. If I write int x4, then the binary pattern that's stored in that int is equal to the decimal value 4. But if I store the character 4, its internal representation is 52. So they're not the same thing. Here's the capital letters of the American English alphabet. the lowercase characters. And then you can see another or a bunch of other characters that you're used to off your keyboard. So that's 128 characters out of the 256 that can be stored in a char. So what could be stored in the other 128? We also have extended ASCII. And so notice this has some symbolic symbols, like for creating real crude tables. So these would be bars around the table. But you also have some accented letters that can represent some languages. But you're not going to represent all known languages using these characters. The closest you'll get to that would be to use Unicode, which is also a character set, but it can represent tens of thousands of different characters. Internally, we still have a number, even if we say we want to store a character. It's just that the characters are easier for a human to read and know that that's what they're working with. So here I create two chars. For this one, I say it's letter A, and I give it a lowercase a. For this one, decimal A, I give it 97. Looking back at the ASCII table, I can see that lowercase a has an ASCII value of 97. So internally, both of these are the same. To prove that to you, I'm going to print letter A twice. The first time I print using %d, which is the format specifier for an int. The second time I use %c, which is for a character. There's 97, there's little a. Then when I want to print decimal A twice, I do the same thing. %d, %c, and I get 97 and lowercase a. So internally, these are no different. The binary equivalent of 97 is used in both cases. Because a char is an integer type, we actually can do math with it. And if we go back and look at the table, we can see that there's a relationship here between the uppercase characters and their corresponding lowercase characters. Capital A has an ASCII value of 65. Little a has an ASCII value of 97. So 65 plus 32 gives me 97. 66 plus 32 gives me 98. 90 plus 32 gives me 122. So each character differs by 32 when we're talking about the uppercase version or the lowercase version. So here I'm going to store capital A, which internally has an ASCII value of 65. Down here, when I write uppercase plus 32, I'm really writing 65 plus 32 to get 97. I assign that to lowercase. And now when I say print the character lowercase, I see lowercase a. So now we're ready to talk about strings. Some programming languages have an actual string type. So to create a variable that's a string in some other languages, you might say something like string and then string name as the variable name. C, however, does not have a string type. And by type, I mean things like ints and doubles. Those are built-in types. But there is no built-in string type in C. So instead, what we do is create arrays of characters. So if I want to create an array with 15 ints, I would say int, array name, and then in square bracket 15. Well, here I'm creating an array that can store 10 chars. So here's the variable type of each of the character of each of the things stored in the array. Whenever I talk about a string, though, in C, it's not just an array of chars. It's a null terminated array of chars. So what does that mean? What that means is at the end of the characters that I want to store, I need to also make sure that there's a null character, which has an ASCII value of 0. Don't confuse 0 here with 0 here. This is the 0 character, and internally its ASCII value is 48. But a null has an ASCII value of 0. And the purpose of that is so that way the computer can know where do the characters stop that represent the string. Now, if I want to write it on paper, or if I want to represent the null inside my programming logic, I write it like this: single quote, \0, single quote. So why is the backslash there? Why not just say quote, 0 quote? Because if I write single quote, 0 quote, I'm talking about the zero character. Just like if I say single quote, little k, single quote, I'm talking about lowercase k. By writing it like this, you can say that I'm escaping the zero. That's escape, E-S-C-A-P-E, which means treat the character that follows the backslash in a manner that's different than you would normally treat that character. We've been doing the same thing every time we wrote \n to get a new line when we printed something. The printf function would see \n, and it knows that that says, oh, don't print the letter n, instead print a new line at that spot. So now we're ready to store strings. One way to do it would be what we see here in B. Because it's an array of characters, I can put in those individual characters. And in fact, I don't even have to use the characters as we're used to writing them. I could look up what the ASCII value for little d is, look up what the ASCII value for little o is, and so forth. But that'd be a lot of work. I'd much rather just type in the letter as I think of it. But this array here stores lowercase d, lowercase o, lowercase g, and then a terminating null. And these are all chars, so they're in consecutive memory locations. That is, they're 1 byte apart. All right? This, though, takes a lot of work as compared to this. I'd much rather write in double quotes DOG. But remember, when I do that, the computer's still going to automatically insert the terminating null for me. So if I were to look at the internal representation of each of these strings, they both would consist of 4 characters, DOG null. And a lot of the bugs that people make when using strings is to forget that this doesn't have 3 bytes of memory, it uses 4 bytes of memory. At times, instead of creating an array like this, we may wish to create what's called a string literal. This is still a null terminated array of characters, but the difference between this and the previous slide has to do with where it's stored at and what I can do with it. I can change these 3 characters if I want, because it's still just a normal array. So the D is at position A0, the O is at position A1, the G is at position A2, and I can change any of those. This string literal is stored in a spot in memory that I should assume I cannot change. I think technically the C standard says that how it's stored is implementation dependent, but I should assume that I can't change it. So how do I find it? I can create a pointer to the first character in the string, and that's what I've done here, char star P. But never forget that P contains the address of the lowercase t. It does not store any of these characters, including the t. But once I have this, then I can print the string pretty much the same way I would other strings. So when I write print %s p, it prints this as a string literal. And I can print the first character of that string if I want by using p0. Or I could print the 5th character, which would have me write p4, right? Because they start indexing at 0. p4 would give me the 5th character, which is the space. I can do all that just like I would a normal string. Because p is a pointer, I can reassign it to point to another string. Whether it be a string literal or a normal character array, doesn't matter. But I can have it store the address of another string. So here, when I say print p, I'm going to print this as a different string. What I should never do, though, is try to change one of the characters in the string literal, like I did here. So let's see what happens when I attempt those things. Let's create a normal array of characters. Normal string. I don't actually know what the name of this is other than just it's an array of characters. So there's those 2 strings. So I print them, that's no problem. I could do this. Print the 6th character, because it's at index 5. So you get the L, you get the G. That, of course, should be in the same column because same index. I can do this. In fact, let's print the whole string just to show you what I changed. Whoops. Oh, forgot the semicolon. You see now I replaced the lowercase g with x, so that was fine. But here's where I run into a problem. We already saw that I can reference, so that should be B. I can reference B5, so I can look at this, I just can't change it. So let's try to compile it and see what happens. It compiles fine, that's not a problem. But now what happened? Segmentation fault. If you program very long in C, you should get used to that phrase, and it's never a good thing. Segmentation faults are memory-related issues. In particular, trying to change something that doesn't belong to you. Normal string is stored in a spot of memory that I'm allowed to change, which is why I can do A5 equals X. But I should assume that B here, well, actually B I can change, but I should assume that string literal is stored in a spot in memory that I cannot change. I'm not allowed to. So by trying to change it, I generate a segmentation fault. But like I said a moment ago, you're going to see this phrase a lot if you program very long in C. Let's see if I do this. B is equal to A. I can do that. Now we'll print B. And of course, B now just points to A, but now that B contains the address of a normal character string, I can do something like this. We'll change the first character, not that it matters. Capital Z. And there it is, Zormax. So when I contain, or when I have a pointer to a normally created character array, I can alter that array within its space. How much space is here? Enough to store normal, space, string, terminate null. But I should not attempt to change a string literal. We can also have arrays of strings, but when we do that, typically they would be constructed using string literals. So how do I create my array? Here's the array name, and it says I'm going to store 4 things. Those things are type char star. So here I have comments, so I put each of the string literals on a separate line just so I can insert the comments. But I could have, without the comments, could have written this, comma, and then on the same line is, comma, on the same line a, comma, on the same line string. That doesn't matter. But never forget that these are string literals, which means that text does not store any of these characters. Because they're type char star, the 4 things stored in this array are the address of the T here, the I, the A, and the S. And just like we saw in my program over here, I can change the addresses that I store. So after this, if I wanted to, I could say text2 equals dog. That would be fine. It's going to create a brand new string literal, so it's not even overriding any of these. It would be stored in a separate place or separate memory than what any of these individual characters is. So I can't change any of these no more than I could change what I saw earlier. I can print these strings by printing the individual characters if I want. So how does this work? The outer loop goes from 0 to 3. And the 0 gives me the address of the t. That is, I have text 0 gives me the address of t. Text 1 is the address of the I. Text 2 is the address of the A. And text 3 is the address of the S. Once I know where the character array begins, then the internal loop begins moving across the string. And notice the test condition here. This is still something that has to evaluate as true or false, but it's different than what we're used to, which is typically things like this. Text IK gives me a character. And so I'm asking the question, is that character equal to the terminate null? If the answer is no, it's not a terminate null, then I print the character. If you saw one of my videos that talked about pointers and arrays, I talked about the difference between pointer notation and subscript notation. This is subscript notation, but I could have written instead of this right here, which is the pointer notation. This right here, I think, better explains how this is working. So if you don't understand this, go back and review that video. But this allows me to print all the characters in this, and then when it finally gets to the terminate null, this fails. So now I return to the outer loop, increment by 1, come in here, and start over on a new string. This is not the typical way, though, you print this string. This just shows how I can interact with the characters. And I would really only do this if I cared about getting individual characters. Instead, I can do this. Here's the same array of string literals, but now I say print each of those. Print F, like we saw in this function right here. When I say print S and I write A, because A is an array, this automatically gives me the address of the first thing that's stored in my array, or the first element. What's the first element of this array? The first element is a character. So I'm providing an address of a character. So it's really a type char star. And %s expects that this is the address of a character that begins a null terminated array of character. Otherwise, it wouldn't know how to stop. So here I'm giving it the address of a null terminated array of characters. So first I give it the address of the t, and then it prints those. The address of the I, it prints those. The address of the A, it prints that string. The address of this S, it prints that string. So this is the normal way of printing string literals. So this was an introduction to strings. I'll create another video in which I talk about some of the more commonly used string library functions. The string library in C is not very robust, meaning it's somewhat simplistic as compared to some other more modern libraries, but it still will make our life easier, so you want to learn to use some of those functions.